Hello everyone, my name is Tirthankar Choudhury. I work in the National Center for Radio Astrophysics and I am going to talk about cosmology. Before going into the details, let us understand what do we mean by cosmology. Cosmology refers to the study of the universe as a whole. We want to understand how the universe was born, how it evolves and what will be its fate in the near and far future. You can understand that this is possibly one of the oldest branches of science, as this is related to a question which human beings would have asked very early. Where did we come from, who are we and where are we going? The cosmology and also astrophysics in general is very different from other branches of physics in the sense that we cosmologists cannot perform any controlled experiments. We have to do with whatever the universe has given us, whatever we observe in the sky, and with that we have to go ahead and try to build our theories and try to understand what is going on in the universe. The picture here tries to show you the current understanding of our universe, which is based on the hot Big Bang model, where the universe has a beginning, it expands and probably will go on expanding forever. And during the lecture series, I will try to give you some idea about what we know about this universe, how did we know about it and what to expect in the future in this research area. Before coming into again details of cosmology, let us set our idea about various scales. Let us start about the sizes and distances we observe in the sky in our universe. Let us start with the solar system. Many of you would know that the solar system, the distance between the earth and the sun is one astronomical unit, which is typically of the order of 10 to the 8 kilometers. Of course, the size of the solar system is slightly larger than this, but this is a number which is good to keep in mind, 10 to the 8 kilometers. In the next stage, let us think about the nearby stars, the stars which are like our sun but far away from us. These nearby stars have distances of the order of 10 to the power 13 kilometers or more. So, we use a different unit of distance when we talk about stars, we call it a parsec. A parsec is defined as 3.1 into 10 to the 13 kilometers and the nearby stars are 1 parsec or few parsecs away from us. The next stage is a galaxy, because stars are not randomly distributed in sky. They come in groups and these groups then form what we call the galaxy. In this picture you would see a typical spiral galaxy like ours, the Milky Way, and the size of the galaxy is typically of the order of tens of kiloparsecs. The distant galaxies on the other hand is on a different scale altogether. The galaxies which form the basics of the universe are more than a megaparsecs or few tens of megaparsecs away, which I have tried to show in this figure. What about the mass scales? Let us start with the stars like our sun first. The sun has a mass which is denoted by this symbol, solar mass, which is of the order of 2 in times 10 to the 33 grams. A galaxy like ours contains billions or few billions of stars. So, the mass of the galaxy would be somewhere around 10 to the 9 to 10 to the 11 solar mass. Of course, galaxies come in various shapes and sizes. So, this is just a typical number to keep in mind. The galaxies also group together and form something called clusters of galaxies. They are of course much more massive. They can be of the order of 10 to the 15 solar masses or even more than that. So, now you have some idea about the kind of distance scales and the mass scales we will be talking about when we are doing cosmology. What about beyond that? If we see in our sky, we find that the galaxies are, as I said, not uniformly or randomly distributed. They form what we call the large scale structure. If you see this picture actually shows a slice in the sky, and this axis tells you the distance from us in billion light years. Each point in this picture is a galaxy, each blue point is a galaxy, and as you can see, the galaxies have some structures. There are more galaxies here, you can see something like a wall here and so on. So, this is often known as the cosmic web or the large scale structure of the universe, and this is something which we want to understand very well when we do cosmology. Just remember the distance scales here. We are now talking about billions of light years, and 1 light year is just 0.3 parsec. So, effectively we are talking about billions of parsecs in this case, the distances. The other thing to keep in mind is that when we observe distant objects, because the light travels with a finite speed, observing distant objects lets us observe the universe at early times. This is often called cosmic archeology. So, let us try to give some examples. So, what I have tried to plot here are different objects in order of their distance. So, we start with the sun, which is a closest astrophysical object, then the nearby stars, then probably our own galaxy, and then distant galaxies. Along this axis, I show the time taken for light to reach us from these objects. So, for example, when we observe the sun, we are not observing the sun now, we are actually observing the sun how it was 8 seconds ago, because that is the time taken for the light to reach us from the sun. If we go to nearby stars, we are talking about years ago. Okay. If we go to the galactic center, we are talking about few tens of thousands of years ago, maybe 10 to the 5 years ago. The distant galaxies, of course, when we observe, we are observing them a billion years ago. So, you can see as we observe things at larger and larger distances, we are observing them as they were at very early times, and this is how we plan to understand how the universe evolved from its young stage to where it is now. Now, when we actually try to understand cosmology, we have to make some basic assumptions. Now, the first one of that is what I call the cosmological principle. In very simple terms, we say that our location in the universe is nothing special. So, any other place in the universe is as similar to us. This leads to the concept of homogeneity. What it essentially says is that when we average the universe over very large scales, maybe tens of megaparsecs, maybe of the order of hundreds of megaparsecs, we think that the universe has the same physical properties at every location. Of course, it does not have the same properties at every location if we see just around us, but the claim is that if we average or smooth over very large scales, this is indeed the case, that every place looks the same. The second principle, which is very useful, is the concept of isotropy. This says that when averaged over again the same very large scales, hundreds of megaparsecs or so, the universe looks the same at all directions. In other words, when smoothed over large scales, the universe does not have any special direction. So, that is what we call isotropy. These principles will set up modeling of cosmology or setting up of the cosmological model as we understand. The next sets of observations which are very useful in building the current understanding of cosmology comes from a person called Edwin Hubble. He around 1929 was doing observations in the Mount Wilson Observatory. He found a way to actually measure distances to, at that time what he called nebulae, to actually galaxies which are beyond our own Milky Way. So, when he calculated the distances, he found that they had distances well beyond the Milky Way. So, now today we understand that actually what he was observing were the other galaxies. So, to summarize, Hubble could actually measure the distances to nearby galaxies beyond the Milky Way. This is what I already said, these objects are the distant galaxies as we know today. Hubble could also calculate the velocities of these objects using the Doppler effect of light, in other words the redshift. So, he measured the wavelengths of spectral lines and compared it with the wavelengths as one would measure in the laboratory, and just looking at the wavelength shift he could calculate the redshift, this z, which he interpreted as the velocity using this relation. So, delta lambda by lambda is v by c, which is also same as z. In general, z can be positive or negative. If an object is moving towards us, then z will be negative. If the object is moving away from us, then z will be positive. What Hubble did next was to plot the velocity and the distances to the galaxies in a 2D curve. The points are shown here, and what Hubble found was that he could fit it as a linear relation. The linear relation of Hubble was that c times the redshift, which is nothing but the velocity, is some constant times the distance. This is usually known as the Hubble's law. The constant we denote it by h naught, and this h naught is known as the Hubble's constant. Hubble at that time measured h naught to be 500 kilometers per second per megaparsec. This means that if there is a galaxy 1 megaparsec away, that would be moving away from us with a velocity 500 kilometers per second or of that order. Now, we have measured many more galaxies and we have refined these measurements. The presently accepted value is not 500 kilometers per second per megaparsec, but it is somewhere around 70 kilometers per second per megaparsec. So, the value of the constant has changed, but this linear fit still remains, and this again, as I said, we call it as Hubble's law. Around the same time, there was another scientist called George Lemaitre. He was working in Europe and he published a paper in 1927, it is actually 2 years before Hubble's results, where he also found this linear relation, and he could also measure this proportionality constant h naught, where he used the published data that were available on distance and redshifts to these galaxies. The original papers was published in French and later translated in English in 1931, but this shows that in addition to Hubble, Lemaitre also independently got this result, and if at all maybe earlier than Hubble. So, it turns out that this was discussed in the community very recently during the 30th General Assembly of the International Astronomical Union IAU just a few months back in August 2018. The scientists, the astronomers put forward a draft resolution to rename the Hubble law as the Hubble-Lemaitre law. This was proposed to recognize Lemaitre's research on the expansion of the universe and to pay tribute to both these scientists for their fundamental contributions to the development of modern cosmology as we understand. In fact, all members of the IAU were invited to participate in an electronic vote, and after the electronic vote the resolution was accepted. So, from now on we should call the Hubble's law not as Hubble's law, but Hubble-Lemaitre law, but as you can understand this happened very recently. So, all textbooks or papers you refer to will probably still show it as Hubble's law, but soon people will probably start using a different name for it. It will be called Hubble-Lemaitre law. Now, you can ask a question. So, Hubble observed many galaxies all around us, and all these galaxies seem to move away from us. Now, you can ask, does this violate the cosmological principle? If all the galaxies are moving away from us, it seems to imply that we are some kind of at a center of the universe and everything is just moving away from this center. So, then does this violate the cosmological principle where we claimed that no location in the universe is special, particularly our location is definitely not special in the universe. Hubble's law seems to indicate otherwise. So, we seriously need to ask the question that does Hubble-Lemaitre law contradict the cosmological principle? It turns out that it does not, and it is not very difficult to understand. To do that, you can ask that if there was an astronomer sitting in some other galaxy and tried to do the same observations, what will they get? So, to do that, let us consider any two galaxies A and B moving away from us O, that is where we are sitting, and they are moving away from us in accordance with the Hubble-Lemaitre law. In other words, the galaxy A has a velocity VAO, which is given by h naught times the distance to the galaxy from us, which is RAO, and a similar expression holds for the galaxy B. Now, let us go to the reference frame of say any of the galaxies, let us take it to be A. So, now we are asking the question, what happens to the observations done from galaxy A? Observer sitting in galaxy A will measure the velocity of let us say B like this. So, they will measure a velocity which we call as VBA, that is nothing but the relative velocity between B with respect to O and A with respect to O. This is nothing but the standard Newtonian addition of velocities. So, VBA will be given by VBO minus VAO. We already know that VBO and VAO, the velocities are related to the distance by the Hubble's law in our reference frame. So, I replace the V's by the corresponding Hubble's laws. So, this becomes h naught times the difference vectors between RBO and RAO, but from this diagram you can already see that RBO minus RAO is nothing but RBA, which is nothing but the distance vector between B and A. So, an astronomer sitting at A observing B will find that the velocity of B is nothing but the same h naught times the distance to B, which is nothing but the same Hubble-Lemaitre law, but now written in the reference frame of A. This tells you that the fact that we observe galaxies moving away from us does not make us special. In fact, all other galaxies observe the same thing. Okay? A galaxy A, which can be any other galaxy, also observes V moving away from us and also the other galaxy B moving away from us, and so the other galaxies and so on. So, Hubble's law does not contradict the cosmological principle, which is a great thing. Okay? So, we can live with the cosmological principle, and the fact that we are nothing special, our location is nothing special in the universe still holds. Okay? So, Hubble's law or the Hubble-Lemaitre law does not violate homogeneity. Now, Hubble's law, if we think a bit more, it already tells us that the universe must be expanding. If the galaxies are moving away from each other, all galaxies see the other galaxies moving away from them. So, this tells us that they were closer at early times. So, which means the universe must be what we call expanding. So, this gives rise to the picture of the expanding universe, and that is something very significant for modern cosmology. We live in a universe which is expanding. In fact, at sufficiently early epochs, we expect the distances between galaxies to go to 0, which means all galaxies, all points in the universe were infinitesimally close to each other. Basically what we are saying is, if the galaxies existed till very early times, they would be kind of on top of each other. Okay. This forms the basis of the presently most popular model of the universe, the so called Big Bang model. In this model, the universe is believed to have a beginning, during which the universe was probably contained in a very small region, maybe within a point, and from that point it has started expanding, and it is expanding even now, which is we are observing them as Hubble-Lemaitre law. Not only that, if the universe was smaller in the past, it also must have been hotter. This is something you understand, that if you take a container and reduce its volume, the temperature will go up. So, the same thing must have happened to our universe as well. Since the size was smaller in the past, the temperature would have been higher. So, not only we call the model as Big Bang model, we just expand it a bit and call it the hot Big Bang model, where the universe starts from a very small size and expands like this. At early times the temperatures were high, and they can be very high, as we will discuss later in some lectures. This would lead us to very interesting physical phenomenon, and it would be very interesting to understand what they imply for the universe or the Big Bang model of cosmology. Now, what I told you till now, the Hubble's observations and cosmological principle and so on, all these need to be put in a sound mathematical background to make any progress. What do we want to understand? We want to understand the large scale properties of the universe. Now, a large scale properties of the universe can only be mathematically modeled if we have a theory of gravity, that too a relativistic theory of gravity, because we are talking about such large scales that simple Newtonian gravity will fail to work. Now, we have a candidate theory which can serve our purpose, and that is the Einstein's theory of general relativity. The basic idea here is that matter tells space how to curve, and at the same time space tells matter how to move. So, there is this constant communication between matter and the underlying space, and that forms the basis of general theory of relativity. This is a very successful theory. It accounted for various things, starting from the perihelion shift in the orbit of Mercury, and also the bending of light of a distant star by the sun. Both of these, by the way, were unexplained in Newton's theory. It has various applications, starting from black holes to gravitational waves to cosmology, and in our case third part is what makes it most interesting. So, let us try to do some mathematics and try to work out the theory of cosmology. So, what is our basis? Our basis is the fact that at very large scales the universe is homogeneous and isotropic. In other words, the space time we are considering needs to be homogeneous and at the same time isotropic, and we want to build a model for that. To start with, let us consider a set of observers for whom the universe does seem isotropic. Observers who are moving with respect to these observers will not find the distribution isotropic, by the way. Only these set of observers will find the universe isotropic, and we call them fundamental observers, or they are also known as the cosmological observers. Now, we want to write, or we want to understand the space time applicable to these observers. Now, in general relativity, the properties of a space time is usually described by an appropriate metric. A metric which I write is as ds square can be expanded as follows. If you have a time coordinate, then the first term will contain a g naught naught dt square. Then there will be a term which will be the cross term of the time coordinate and the spatial coordinate, and the corresponding metric element is called g 0 alpha. And then there is the spatial part of the metric, which I have written as g alpha beta dx alpha dx beta. Remember, in these lectures alpha and beta take values 1, 2 and 3. So, alpha beta denote the spatial part of the metric, and we have employed the Einstein summation convention. For example, in this term, this expression is actually summed over both alpha and beta. This expression is summed over alpha. In the convention I am working with, I have assumed the metric signature to be +1, -1, -1, -1. Different textbooks, different papers employ different kind of conventions here. So, you need to be slightly careful what convention you use, and you should be able to convert expressions from one convention to the other. That will be very useful in general. Now, of course, this is a general metric. It contains all the metric elements, and all the metric elements can in principle depend on the time coordinate and the spatial coordinate. But we want to write a metric for a homogeneous and isotropic space time. So, maybe we can do some simplifications. First, we claim that if the universe is isotropic, this cross term, this g 0 alpha should go to 0. If not, you can define a vector, say v alpha given by g 0 alpha, and this vector will give a preferred direction to the observers, and that will then violate the isotropy of the space time. So, if we want to conserve isotropy, this g 0 alpha needs to be put to 0. So, you can see we have already started simplifying this metric. Now, before we go forward, what I do is I write g alpha as minus, let us say, sigma alpha. This is just to remind ourselves that this part of the metric will actually come with a negative sign because of the signature I have adopted. I have done nothing very fundamental or very serious here. Okay. The next thing is to choose an appropriate time coordinate. Now, the most appropriate time coordinate for these fundamental observers or the cosmological observers would be what we call the cosmological time. In other words, in the rest frame of these observers, the proper time would simply be given by ds equal to c dt, and that allows us to put g 0 0 to 1. If we can do that, we can write the metric in a much simpler form. ds square becomes c square dt square, because we have put g 0 0 to 0, minus sigma alpha dx alpha dx beta. You can see the cross term has vanished because of isotropy. Now, let us see if we can simplify this a bit further. Both homogeneity and isotropy would further demand that sigma alpha beta, which in general can be a function of time and position x, must be decomposable into a time dependent function which I call s square t times a function h alpha beta which only depends on x. Now, this is not very easy to understand. You can very easily get this by, for example, taking a triangle and realizing that homogeneity and isotropy would imply that the shape of the triangle cannot change, only its overall size is allowed to change. In an expanding universe, the overall size should increase. If you just consider this as a toy example, you should be able to show that the sigma alpha beta decomposes into a time dependent part and a position dependent part. So, let us now then write the metric as c square dt square, the first term, and second term I write it as s square dl square, where dl square is nothing but the line element for the 3-dimensional space, and that is nothing but h alpha beta dx alpha dx beta. So, of course, this is summed over all alphas and betas. Remember, h alpha beta depends only on x, because the time dependence have been taken into account by this term, which is the s square t. Now, let us make further progress. Since the 3 space is isotropic, we said that no direction is spatial. It is natural to use the spherical polar coordinates r theta phi. Now, the most general metric which is rotationally invariant, in other words it does not distinguish between directions, is given by this, which is dl square equal to dr square divided by some arbitrary function which I call f of r, plus r square times d theta square plus sin square theta d phi square. Now, this r square d theta square plus sin square theta d phi square will be very familiar to you. This is the part of the angular part of a metric when written in spherical polar coordinates. The only non-trivial thing is this f r, which probably you would not have seen. Of course, if I put f r equal to 1, this would simply represent the flat space. This dl square will then simply be our standard Euclidean space, which is dx square plus dy square plus dz square in Cartesian coordinates. F r, when it is not equal to 1, it actually indicates that this space has a curvature, it is not flat anymore. So, this f r generalizes our standard Euclidean flat space to something which can account for curvature of the space, and that is the most general thing we can deal with. So, you can already see we have simplified the metric quite a bit. The metric, the total metric can be written like this, a c square dt square minus a time dependent part times dl square, and dl square is obviously quite significantly simplified now. Now, what do we do about this function f r? We can do a bit more. What we do is, we take this 3-dimensional space and calculate the scalar curvature of this 3-dimensional space. Remember, this is not the scalar curvature of the full metric, no, it is just the scalar curvature corresponding to the metric of this 3 space. Now, this is a standard exercise in general relativity or tensor analysis. You can calculate the scalar curvature and show that it is given by the simple expression. Okay. It involves derivatives of this function f and these terms. Now, if the space is homogeneous, then this scalar curvature, which is independent of the coordinates I choose, must be independent of at what position we are. In other words, the scalar curvature needs to be independent of r theta phi, the position coordinates. So, what we do is, we set this r, the scalar curvature, to be a constant. I could have taken the constant to be some k, but let me take it to be 6k, because this will help me in simplifying some expressions later on. So, let us set this scalar curvatures to be 6k and then try to solve this differential equation in f. What you will find is that this f will turn out to be just 1 minus this constant k times r square, where we have used a boundary condition that as this k goes to 0, f should be 1, because we know that when k goes to 0, the curvature goes to 0, and we have already discussed that when there is no curvature, this function f must be 1. Okay. So, that boundary condition has already gone into this function. Now, we just put everything back, and you have to do some smart rescaling of the coordinates and also this function s. If you do that, what you find is that the full metric takes this form. ds square is the time part, the c square dt square part, minus s square of t times the spatial part of the metric, which has dr square divided by 1 minus k times r square plus the angular part, which was what it was before. I have introduced a new parameter small k, which is very closely related to the curvature, this capital K, by this formula. It is nothing but k divided by the magnitude of k. So, the small k essentially can take only 3 values. It is plus 1 when capital K is greater than 0, it is minus 1 when capital K is less than 0, and the small k is 0 when capital K is 0. So, of course, small k is 0 means that there is no curvature in the spatial part of the metric. Okay. This metric has a name. It is known as the Friedmann-Lemaitre-Robertson-Walker metric, FLRW metric. So, I will keep on using this term FLRW metric throughout the lecture course. Sometimes it is also known as FRW metric. This Lemaitre is sometimes not included in the list. So, if in any book or in any lecture course or in any website you see FRW metric, you know they are also talking about the same metric. Okay. The importance of the metric is that this is the most general metric which is consistent with homogeneity and isotropy of space time. Okay. No other approximation has gone in defining this metric. This metric you can see contains basically 2 parameters. One is this function which is s of t. This is known as the scale factor. It characterizes the expansion or contraction, as the case may be, of the universe. Our universe is always expanding. So, this s actually characterizes the expansion of the universe. There is another parameter which is this dimensionless constant k. This characterizes the curvature of the 3-dimensional space. For flat space, we need to put this k to be equal to 0. If there is curvature, k will take appropriate values plus 1 or minus 1. This metric can also written in a slightly different form, and depending on the context, one form or the other is more useful. This has to do with changing the radial coordinate to something else. So, let us introduce this new coordinate chi, which is nothing but integration over dr divided by square root of 1 minus k times r square. So, you can see the result of this integration will depend on the value of k. So, this result we denote this as some s k inverse of r, where this s k inverse of r is defined as sine inverse r when k is equal to 1. It is sine hyperbolic inverse of r when k is equal to minus 1, and it is just simply equal to r when k is equal to 0. You can put in these values of k here, work out the integral and see that these are indeed the cases. Now, if this is the case, what I can do is I can replace r by just sk of this new coordinate chi. So, what happens is my metric now becomes the same thing, ds square is c square dt square minus the scale factor square, that remains, but instead of this dr square, now we write the metric in terms of d chi square. So, there is a d chi square term, and then the angular part has a somewhat more complicated expression. It comes with the sk square of chi. Now, this sk can be either sine or sine hyperbolic or simply this chi, depending on the value of k or the curvature. Let us now spend a bit of a time understanding what I meant by this spatial curvature. For example, if I take the flat case for k equal to 0, the spatial part of the metric is nothing but dr square plus r square d theta square plus sin square theta d phi square. This is nothing but the flat Euclidean 3 space, okay, and that is shown by this picture, okay, just flat geometry. This would correspond to k equal to 0. For k equals to 1, the metric takes this form. I am not repeating it, but you can work out that the metric will have this form. This actually represents a 3 sphere which is embedded in an abstract 4-dimensional Euclidean space, and the volume of this entire space is finite. One has tried to show this by, schematically by this sphere, which shows a closed geometry. So, whenever k is equal to 1, we call the universe as closed. Okay. The other case, which is k equals to minus 1, corresponds to the open universe. The metric takes a form which is this, you have put k equals to minus 1, and this essentially represents a 3-dimensional hyperboloid which is embedded in an abstract 4-dimensional space. Okay. So, that hyperboloid is been indicated by a picture which looks like this. This corresponds to open geometry. For example, the volume of the entire space is infinite as opposed to what you get for the closed space. So, that is why this space is known as the open universe. We can take a bit of a time and see what we can do with the metric. Just remember that most recent observations indicate that our universe is very close to being spatially flat. In other words, k is very close to 0 as far as the present universe, present observations indicate. Now, what happens to the Hubble-Lemaitre law? So, to understand that, we have to understand the concept of redshift in this universe. In other words, we have to understand how the redshift arises in the FLRW metric. So, to do that, consider a galaxy at a coordinate r or chi. Now, you can choose which coordinate you want to work with. So, it is at a distance r or chi from us, because we are sitting at r equal to 0, which is same as chi equal to 0. So, we are kind of at the origin of our coordinate system. Let this galaxy emit an electromagnetic wave of frequency nu. Now, this electromagnetic wave will come to us as photons radially, and the propagation of this electromagnetic wave is governed by a equation where we put ds square equal to 0. If you do that, you will get an equation which will relate the coordinate chi to t. So, d chi dt will be minus c by the scale factor, where you could have chosen either the plus or the minus sign. We have chosen the negative sign because that implies photons which are coming from a distance to us. Now, you consider a wave crest of this electromagnetic radiation emitted at t from this galaxy at chi. Let us say at t it emits a wave crest like this. We, the observer, receive this signal at an epoch t naught. Okay. We receive this wave crest at some epoch t naught, which will be after t, of course, because light will take some time to come to us. The next wave crest is emitted at a slightly later time, let us call that t plus delta t, which is this, and that is received at the earth at the time t naught plus delta t naught, okay, which is indicated here. Now, the distance of the galaxy or the coordinate of the galaxy with respect to us remains the same during the emission of the two wave crests. So, what I can do is I can integrate this equation, this differential equation, either from t to t naught, which will correspond to the propagation of the first wave crest, or I can integrate from t plus delta t to t naught plus delta t naught. that would correspond to the propagation of the second wave crest, and both these wave crests have travelled a distance chi. So, if that is indeed the case, we can write a equation which looks like this: chi is equal to c times integral t from t to t naught dt over st, which is nothing but just the solution of this equation, and that is same as this expression as well, where just the integration limits have been changed. Now, if the scale factor does not change significantly over this time interval delta t, which is indeed the case, what we can do is we can actually simplify this integral drastically and actually show that delta t by s of t is equal to delta t naught divided by s naught. Now, the frequency of the light wave nu is nothing but 1 by delta t. So, that can be seen from this picture. The time difference between the emission of the wave crest is delta t. So, the frequency will be 1 by delta t, and that will be the frequency at which it was emitted. The frequency at which we received will simply be 1 by delta t naught. Now, if that is the case, we then obtain that the frequency at which we receive the light divided by the frequency at which was emitted is nothing but the ratio of the scale factors. You can convert it into the ratio of the wavelengths and the relation will just invert, nothing else. Okay. We have already talked about the redshift earlier. In this case, the redshift is defined as the difference in the wavelengths divided by the original wavelength, which is nothing but lambda naught by lambda minus 1. Using this expression, we see that the redshift is essentially related to the ratio of the scale factors by this relation s naught by s. This implies that if we can measure the redshift of a light signal originating from a very distant galaxy, we can in fact estimate the size of the universe, of course related to today when the signal was originated. So, this actually is the starting point of observational cosmology, where you observe a distant object, you measure the redshift, and from that you understand what was the size of the universe, and as we will later see, we will understand a lot more just by measuring the redshift. Just to summarize again, the redshift is the ratio of the scale factors. Now, you can see higher redshifts means smaller values of s, which means earlier epochs. So, if you observe objects with higher and higher redshifts, you will be observing them as they were at much earlier and earlier times. Not only that, higher redshift, since it implies earlier times, it also implies more distant objects. This is nothing but the cosmological archaeology which we were talking about earlier in this lecture. So, as you can see, just by measuring redshifts, we can understand cosmology quite a bit. We can observe the universe at earlier times, and hence we can also observe objects which are at very large and large distances. So, this would be the good time to stop. We can wrap up the first lecture, and in the next lecture we will try to understand more about this FLRW metric, and we will carry on our discussions there.